So it says a large cube with each side and units in length where n is more than 3 is made up of white colored styrofoam. This cube is now cut into n cubes, smaller cubes of equal size. Half of these n cube smaller cubes are now painted with red color on all of their 6 faces if n is even. And if n is odd, n cube plus 3 by 2 smaller cubes are painted on all faces with red color. So if n is odd, this is the number of red faced cubes. If n is even, then we have half of them as the number of red cubes. The remaining smaller cubes are painted blue on all their 6 faces. What else? These cubes are then glued back together to reconstruct the initial larger cube of each side of length n units. And then we have some questions based upon it, as you can see 17, 18, 19, 20, 21 and 22. Let's start solving it. Just to make you understand a few things, I have shown you a picture here because this is going to be used a lot many times in the upcoming questions. So first of all, when n is even, half of them are red, the remaining half are blue. When n is odd, n cube plus 3 by 2 of them are red, the remaining are blue. Now I'm talking about a cube here. I hope all of you can see this cube here. And this is showing you the top face of this cube. If you look at the top face, I'm sure it would look like this. Why am I showing this to you? If I just see that this light green boundary is the outer surface of the cube, and this light blue cube is the cube which is completely inside this bigger cube. It is completely inside this bigger cube. So if this outer cube is of n by n by n sides, so this inside cube would be of n minus 2 divided by n minus 2 by n minus 2, because length, breadth and height of that cube would be n minus 2, n minus 2, n minus 2. You can understand it from this other figure. Let's say this is the length of the cube. This is what I'm talking about. It is here. If this is n. Similarly, this is also n. If this is n. If I talk about that blue surface inside, what is that blue surface? So you decrease one from here. You decrease one from here. The length of that would become n minus 2. Similarly, you decrease one from here. You decrease one from here. The breadth would also become n minus 2. So the cube inside would be of length n minus 2, breadth n minus 2, and similarly the height would also be n minus 2, because one would be decreased from the top and one would be decreased from the bottom. This is something that we are going to use again and again in the upcoming questions. So from that perspective, it becomes important for us to understand this. Now let's start doing the question straight away. The first question: if n is equal to 5, at least what percentage of the reconstructed larger cube's total surface area can be blue? Let's talk about it. Question says at least what percentage. So I want to minimize the percentage of the reconstructed larger cube surface area that can be blue. So for your convenience, I have made a cube here. If n is equal to 5, the total number of smaller cubes that can be made is 125. And because n is odd, can I say 125 plus 3 by 2 of them, that is 64 of them, are red, and 125 minus 64, that is 61 of them, are blue. I want to minimize the percentage of this reconstructed larger cube's total surface area that can be blue. That means I want minimum number of them on the outer area. Minimum number of them should be on the outer area. Now, how many surfaces are visible to us on the outer area? If you look at the surfaces over here, I have got a total of 5 into 5, 25 surfaces here. Please keep in mind, surface is different from the cubes, right? A cube actually has 6 surfaces. So I am talking about surfaces now. So it has 25 surfaces on one face, 25 here, 25 here, 25 on that side, 25 behind and 25 in the bottom. So total number of blue surfaces is 150. Sorry, total number of outside surfaces are 150. I want to minimize the blue ones among them. I want to minimize the blue ones among them. If you want to minimize the blue ones, just look at this. How many blue cubes I can put completely inside it? As we just discussed on the previous page, if 5 cube is the total number of cubes in this complete bigger cube, the number of cubes which are inside it is 5 minus 2 cube. We just discussed about this. So 27 of the cubes are completely inside, which are not visible from outside. So what can I do? Because I want the blue cubes on the outer side to be minimized, I will assume all these 27 which are inside, they all are blue. If they all are blue, that means still I have 61 minus 27, which is equal to, I think, 34. 34 cubes would still be on the outer surface. 34 cubes can still be on the outer surface. What can I do from here now? How can I minimize the number of blue cubes on the outer surface? If there are 34 outside, what can we do? We can do one thing, that I'll take these 34 only at those places where they would be giving us minimum possible surfaces outside. What does that mean? If I take this cube as a blue cube, it will give me 3 surfaces on the outside. If I take this cube as a blue cube, it will give me 2 surfaces as blue on the outside. But if I take any of these 9 as a blue cube, they would just give me 1 blue surface. I hope you are getting it. Similarly, I can take these 9 as well. Similarly, I can take these 9 as well. Similarly, I can take 9 on that side and this side. I just need 34. So, of course, I have 54 cubes whose just one face is visible from outside. Out of those 54, I can keep 34 as blue. So, I will see out of these 150 surfaces, those 34 surfaces minimum will be blue. What percentage is this? It is equal to approximately 23%. So the right answer for question number 17 is 23%, which is option B. Now it says if n is equal to 6, at how many faces of the reconstructed larger cube can be completely blue colored? So now he has given the value of n as 6. Now he wants at most how many faces of the reconstructed larger cube can be completely blue colored. I want maximum of them to be blue colored now, right? 6 is an even number. So I can straight away say 6 cube divided by 2, that is 108 of them are red cubes and 108 of them are blue cubes. Now when I talk about a cube with n is equal to 6, how many cube surfaces are visible on the outer surface? How many of the outer surfaces are visible to us? Just the way we did in the previous question, on the outer surface, 25 faces were visible on the outer surface of every face. This time 6 by 6, that is 36 surfaces would be visible on the outer surface. If I just show it to you very fast with a bad drawing, but I'm sure that you would be able to understand that if I just make 6 surfaces here, 1, 2, 3, 4, 5 and 6. Similarly 1, 2, 3, 4, 5 and 6. Same is done here, same is done here. Actually you'll see on one surface you will have 36 faces visible. I hope all of you can see that. 36 faces are visible. Similarly 36 faces are visible here. 36 faces are visible here. But there is an important point in all of them. That important point is that when I make these 36 and 36 surfaces at all these places, see, just let me make it 1, 2, 3, 4 and 5. 1, 2, 3, 4 and 5. 1, 2, 3, 4 and 5 is already there. And 1, 2, 3, 4 and 5 is already there. So what do I see here? Actually, out of these 36 surfaces, if you just look at these 25 surfaces over here, look at these 25 surfaces, right? Similarly, 25 surfaces are here. Similarly, 25 surfaces are here as well. What about the other surfaces? Now, these are 75 surfaces. These 75 surfaces, of course, I can put a blue cube and I can get these 75. But after these 75, some more blue cubes are remaining with me. Even if I put them over here, 5 of them would be needed to cover up these because they would be having two surfaces visible. 5 of them would be used over here. 5 of them would be used over here. And one would be in this corner, right? So ultimately 5 plus 5 plus 5, that is 15. 1 in the corner, 16, plus 25, 25, 25. So 91 blue cubes, if I use them, I can show all these three faces as completely blue. I hope you all are getting my point. By using 91 blue cubes, I am able to show 25 of them, three of the faces as completely blue. What about the others then? Now, after this, I am just left with 17 more cubes. And using those 17 more cubes, I cannot make one more complete face as blue. Question is asking for how many cubes can be completely blue colored. So I see I have been able to make just three faces as completely blue colored. For the fourth one, I would be needing more than that. I would be needing at least 20 more than that. So therefore, with 17, I would not be able to do it. So my answer for question number 18 is 3, that using these 108 blue colored cubes, I can show maximum 3 cubes as blue. Now, what about this 19th question? If all the faces of the reconstructed larger cube are painted blue, then what is the minimum value of n? That means, for what minimum value of n, I can have all the outside cubes as blue. I can put all the outside cubes as blue. For example, let us say n is equal to 4. With n is equal to 4, total number of red cubes would be 4 cube divided by 2, that is equal to 32. These are the red cubes. The total of blue cubes would be 4 cube divided by 2, that is again 32, which is blue cubes. But how many surfaces are there outside? If you remember that, I told you 4 cube is the total number of cubes, out of which 4 minus 2 cube, that is 2 cube, would be inside. So 64 minus 8, 56 cubes are visible on the outer surface. But I have only 32 as blue. So how can they all make the outer surface as blue? It's not possible. Let's check for n is equal to 5. If n is equal to 5, then 5 cube plus 3 by 2, that is 64 of them are red, and 5 cube minus 3 by 2, that is 61 of them are blue. But the number of cubes visible outside is 5 cube minus 3 cube. So it is 125 minus 27 is 98. Even this 98 is greater than 61. How can I make the outer surface completely blue? Let's check for n is equal to 6. 6 cube divided by 2 is equal to 108. 6 cube divided by 2 is equal to 108. And once again, I see 6 cube minus 4 cube, that is 216 minus 64. 216 minus 64, I think it will give me some 152. Still, it is coming out to be greater than 108. It is not possible. Let's take n is equal to 7. So 7 cube 343 plus 3 divided by 2, that is 346 by 2 is 173. And 7 cube minus 3 divided by 2 is 170. But the number of cubes visible on the outer surface is 7 cube minus 5 cube. So 343 minus 125, it is greater than 200. This also is not going to work for us. Let's check for 8. 8 cube, that is equal to 512 divided by 2 is equal to 256. Similarly, 8 cube divided by 2, 256 would be blue as well. So, number of cubes visible on the outer surface is 8 cube minus 6 cube, that is 512 minus 216. It gives me 196. And I think, yes, this is working. Let me check it again. 512 minus 216. So, it is 296. Even this is not working. It is 296. Next, n is equal to 9. So 729, that is 9 cube, plus 3 divided by 2, that is 732 by 2. 732 by 2 is 366. So how many of them are blue? 9 cube minus 2 divided by 2, that is 363. And 9 cube minus 7 cube, it is equal to 729 minus 343. So 729 minus 329 would have been 400, and 400 minus 14 more, it is giving me 386. Even this is greater. Oh God, it's a large question, long question. Finally, when I take 10, it is 10 cube divided by 2, that is equal to 500. And once again 10 cube divided by 2, it is again 500. And how many cubes are visible on the outer surface? It is 10 cube minus 8 cube, 488. Finally, I get a number where I see that the number of cubes visible on the outer surface is smaller than the number of blue cubes, which means the outer surface can be completely covered with blue color. So therefore my answer is 10. This is the minimum number for which it is possible, and this is I think the smallest possible solution according to me. If the number of smaller cubes that are colored red is a perfect square, what is the minimum value of n? Okay, let's have a look at this as well. Number of smaller cubes that are red is a perfect square. So what is the minimum value of n? Let's start with n is equal to 4. How many of them are red? It is 32. It is not a perfect square if n is equal to 5. So 5 cube, that is 125, plus 3, 128 divided by 2. It is 64, and yes, it comes out to be a perfect square. It was already given to us that n is greater than 3. So therefore I have started with 4. It did not give me a perfect square. 5 gave it to me. So my answer is 5 for this question. For which minimum value of n is the number of each type of smaller cubes colored red and blue both perfect squares? So in the previous question he said only red. Now he's saying both. Of course, there is no need to check 5. I'll start with n is equal, sorry, 4. I'll start with 5. I got 64 of them as red, but I got blue as 61. I'm sure you can calculate them by yourself now. So therefore, I'm straight away writing the numbers. 6 cube by 2 is 108, not a perfect square. For 7, 343 plus 3 divided by 2 is 173, not a perfect square. For 8, 8 cube, that is equal to 512 divided by 2 is 256, and this also is 256, and this is the first time when I have got both of them as perfect square. So this comes at n is equal to 8. So this question says n is equal to 9 at most. What percentage of reconstructed largest cube's total surface area can be blue? Almost like the first question, but this time we want to maximize the area that can be blue. Let's have a look at this. Now, when n is equal to 9, first of all, how many red and blue are there? If n is equal to 9, rather I'm just concerned about blue. So blues are n 9 cube minus 3 divided by 2. So 729 minus 3, 726 divided by 2 is 363. So 363 cubes are blue. What is the outer surface of this n is equal to 9 cube? Outer surface is having 9 cube minus 7 cube, that is 729 minus 343 cubes, which is equal to 6 and then 38. So 386 cubes are visible from outside. 363 cubes are blue and 386 cubes are visible from outside. I can keep all 363 on the outside, the remaining ones would be red. But the point is, he's talking about the area. Now, when n is equal to 9, on the outer surface, every face has 81 surfaces visible, and there are 6 faces. So the total number of surfaces visible are 486. I hope you got my point. We did it before as well. That on every surface you have got 81 surfaces visible. So total 486. What can I do? I can put all these cubes on all those places which are at the corners, because corners will be showing me 3 surfaces. On the edges, because edges would be showing me 2 surfaces. The remaining ones can be put into the middle of the surfaces. That means out of this 386, if I subtract 363, what do I get? I get 23. These 23 red cubes can be put on the surface, neither on the edge nor on the corner. So these 23 red surfaces would give me actually 23 single faces which are red. They'll give me 23 red faces. So out of 486, 23 faces are red, which is approximately 5% of the total, right? Because 10% of the total is 48.6. 5% of the total is 24.3. This 23 is very close to that. So approximately 5% of them are red. Question is asking at most how many can be blue. So red minimum are 5%. So blue maximum can be 95%. And that is the answer for question number 22.